Hi, everyone. Let me start by saying that internet censorship practices are pervasive, but it changes from country to country and time to time. And for that reason, many researchers in the field have been interested in measuring it globally and continuously. We can state this problem formally as how we can detect whether two pairs of hosts can talk to each other. And we want to know that for many hosts around the world and many sites. Let's say a Chinese user to a site in Sweden. Current approaches, this is a very hard problem, and current approaches is to put instrumentation in a user's or a site by installing a software, either at the users or handing in a Raspberry Pis or simply renting VPNs. And as you can imagine, these approaches has their own disadvantage. For example, there are not that many volunteers or VPNs to rent. Usually measuring censorship involves some sensitive topics and can increase risk. And last but not least, the data that is being collected are not continuous. Several years ago, Jet Kirandel and I at UNM started to think about this problem differently. What if we can measure whether two hosts can talk to each other remotely from somewhere else around the world? At first, it sounds impossible, but we came up with a technique that's called hybrid ADL scan or a spooky scan. A spooky scan is a TCP IP side channel that, off the path, remotely, can detect whether two hosts can talk to each other, and if not, in which direction the packets are being dropped. Remember, it's off the path and remote. In this talk, we build on a spooky and construct Augur, a system that measures connectivity disruption globally and continuously. Let me give you some background. You all must remember TCP handshake, but one thing you might not remember is in any of the packets that go back and forth, there is an IP ID field, which is a 16-bit bits, and it's being used for fragmentation reason. And I use this IP ID a lot. There is a part of TCP protocol said if you send unsolicited packets to a host, it should respond back with a reset. Another part of the protocol said if you send the same packet to a host with open port, it should send you a SYNAC. And if you don't send a proper ACK or reset, it has to retransmit because TCP is reliable. For a spooky, a user doesn't need to be end user. So from now on, instead of user, I call it reflector. And for a spooky, reflector needs to maintain global IP ID behavior. That means global IP ID, that means the IP ID values have to be generated by a shared global counter and disregard of what the packets goes to, disregard of the destination. By looking at this counter at each time, we can guess how many traffics the machine is generated. So a spooky start by a measured machine, let's say I send a SYNAC packet to a reflector which maintains global IP ID behavior. In response, I will receive a reset, but in that reset, I will see IP ID value, the current value of that. The next step, I send a spoof SYN packet using a reflector IP as a source IP. So site will receive that and obviously send a SYNAC to whoever's on it. Reflector here. Reflector receives unsolicited SYNAC, so it's going to send a reset. Consequently, the IP ID is going to be increment by 1. So when again I ask for IP ID value, I will see a delta IP ID 2. So I can guess that somebody talked to in here in this example site. If I do again ask for IP ID, I won't see any change except my own IP ID query. So imagine a scenario when the site to the reflector is being blocked. In that case, well, none of the packets from the site will get to the reflector. So the changes in IP ID that I will observe is only results of my own IP ID queries. And bear with me, in the next scenario, when the packets from reflector to site is being blocked, the SYNAC from the site gets to the reflector. Reflector will create a reset. Consequently, IP-ID will increment it. And for the first second, I see a jump of 2. Then the retransmission will kick in, and IP-ID again increment by 1. So in the next successive IP-ID query, also I'm going to see a jump of 2. So it will be 2, 2. So let me pull all this together. We have 3 cases and 3 different ways that IP-ID we have for delta IP-IDs, and therefore we can detect them. In reality, the reflectors have other machines or hosts to talk to, and therefore we have to cope with the noise. The simplest, most intuitive way to deal with that is instead of sending one spoof SYN packet, we amplify the signal and send n spoof packets. And for a variety of reasons, packet can get lost, reflector can receive a sudden burst of traffic, so it makes sense to repeat the measurement. There is another good insight, which is not all the reflectors have the same level of noise. And if we want to measure something continually and globally, then we need to exploit that. So put all this together, this is the Augur's probing method. For 4 seconds, I do IP-ID query. And for 1 second, over 1 second, I send 10 spoof SYN packet while I'm watching the IP-ID query. Then I look at the delta IP-IDs. Do I see a jump, a sudden jump? How confident I am that this jump is the results of my own spoof packet? Well, I continue these runs until I'm confident. It turns out there is a statistical analysis that can help, and that's the sequential hypothesis testing, and it can help us to gradually build confidence by repeatedly running and collecting samples. I'm going to give you a very light version of how Augurs uses sequential hypothesis testing, but I refer you to a paper for the details. So, Augur adopts sequential hypotheses by first defining random variables that models how IP-ID accelerates under perturbation that we cause. We also then calculate some known outcome probabilities or priors. Putting all together, then we can formalize an algorithm that helps us to detect the case. The algorithm is basically start by collecting one trial and updating the sequence of values for our random variables, then check these samples of value, what is the likelihood of this sample of value belong to the distribution when blocked happen or does not happen? And we continue that until we reach to a desired statistical significance. Okay, this is how Augur put all these pieces together. Well, first we scan the whole IPv4 to find global IP-ID machines. Then we filter them based on some criteria. For example, all these machines are stable. Given the list of websites that we are interested to measure, we first resolve them and then check whether the hosts are passing some criteria. For example, retransmit enough of SYNAC. Then we run many parallel measurements, making sure that neither the site nor reflectors are being used in the same measurement at a given time. Then we use our statistical analysis and finalize the results. I started the talk by saying that there are 3 key challenges. First, coverage, ethics, and continuity. Augur solved the problem of coverage by offering more than 22.7 million reflectors, potential reflectors. The second best case that we have is less than 10,000 probes by RIPE Atlas. You might, with respect to ethics, you might say, well, Augur creates some traffic from site to reflectors, and it may appear that these two are communicating, and if the site is sensitive, then, well, that can cause risk. Augur reduces risk by running measurement from the routers to hop back from the trace routes endpoint. And even with putting such a harsh constraint, we have more than 53,000 vantage points over 180 countries. Well, how about continuity? Augur doesn't depend on volunteers' connectivity or on reliable Raspberry Pis, so we can run measurement continuously. To summarize, Augur overcomes the key challenges of the previous approaches. To test run the framework, we started by collecting 2,000 reflectors over 180 countries, and we selected 2,000 sites, half of which were sensitive, and there were instances of them being blocked somewhere around the world, and the other half was popular websites. And we let Augur run for 17 days. First thing first, we wanted to validate the technique, and that by itself is very hard because most of the times we don't have ground truth. And we started by saying, let's look at the aggregated results and check whether it matches the reasonable assumption we have about connectivity disruption. For example, one reflector shouldn't show all the sites block or majority of the site block. Sites shouldn't be blocked for many reflectors. And we said we should see block for more bias towards a sensitive block and sensitive sites. And indeed, that's what we observed. Another way of validating is like, can we replicate the previous finding? And that was the case as well. All these validation steps that we did increased our confidence about the accuracy of the technique. So let me give you some highlights of the results. These are the top 6 block sites from site to reflector direction. And an interesting example is Amtrak.com, which is the ranked 6th, and it's being observed being blocked in 57% of countries. And the reason is it's being resolved to the IP that 2 other sensitive domains also being resolved to. And digging further, we found that probably Amtrak is using a cheap DNS service that uses a HTTP redirect. This is the top 6 from the other direction, which is from reflector to site. And you can see NSA.gov stays at the top. And considering the nature of the site, we can probably say perhaps this is being blocked on the site side or server side. And this is a common practice for protecting websites to protect themselves from DOS attacks or following embargo rules. They usually block their services for a specific region. And actually, Augur provides an environment for us to dig further and systematically study this, which is a future work. Well, one can say, hey, what if your technique becomes famous and sensors start to evade it? Is it possible? Indeed, some adversaries can. For example, they can establish a stateful firewall and block unsolicited SYNAC packet. Or they can, for example, let the TCP control packet, but block the data packets. Or simply just block the measurement IP. We believe that for the first 2, implementing such techniques are really challenging, especially in the national level. And for the third, of course, we can mitigate that by periodically changing the measurement machine IP. Augur is great, but it has its own limitation. Although connectivity disruption has a strong indication that censorship might happen, but not necessarily, and we cannot distinguish that. Augur's geolocation accuracy depends on public or commercial geolocation databases. And as you know, when it comes to router geolocation databases are notoriously bad. So there should be a future work about that. And finally, using Augur, we can say that there is a blocking happening between a site and a reflector, but we cannot say in which hop, where in the past the blocking happens. And for example, is it the ISP of the person, government, or the site side? And we need to come up with more techniques to be able to actually guess where exactly happens. Let me summarize the talk by saying that Augur is a system that uses TCP/IP side channel to measure connectivity disruption globally and continuously. And now I'm open to questions. Thank you.
Hi, thanks for your talk. Piers O'Hanlon, Oxford. I was just curious, you mentioned sort of SPF sort of checks, like the source routing sort of stuff, because if you're spoofing packets, it's interesting that you're not seeing that much of an effect from that.
So to be able to spoof packets, you have to talk to your upstreams and make sure that they don't drop your packets. And actually, in 3 universities that I've been involved with, we could actually let the upstream let us be able to do spoof packets. Yes, this is another caveat about a spooky scan or Augur, which is like we are using spoofing in a right or neat way rather than what spoofing is famous for. So.
Thanks, yeah.
You described the challenges a sensor would have to try to defeat your mechanisms pretty well. So how powerful would a sensor have to be compared to the power that, say, China has today?
That actually people ask this question. For example, governments that are have enough of money to be able to spend on their firewalls, wouldn't they do that? So to be able to do that, like establishing a stateful firewall, they have to make sure they are synchronized over the all their firewalls, all their systems. For example, if the SYN goes through traverse another path, or SYNAC goes to other, they have to be able to make sure this happens. And being able to sync at the very real time, that's really hard. And if they just try to establish that, I think it's very impressive.
Right. Yeah, they'd probably try to find where your measurement sites were and find them and block those as you change them.
There are many ways that people can block. For example, it's IP blocking, DNS, and URL or keyword blocking. And as it turns out, like IP blocking is detecting that is good, but the more we traverse towards CDNs, then it's not the right way to block that, because by blocking the IP of the domain, then you're blocking the whole CDN. So yeah, then we move to the DNS level blocking and HTTP blocking or so on.
This particular side channel has been exploited over the years for many things. I'm curious, what is your opinion of the fact that it exists? Is it a severe design flaw in TCP/IP? If you were designing it, would you allow it to be there, or would you provide another mechanism for doing what it is that you need?
Yeah, that's actually a really good question, because it shouldn't be machines that maintain a global IP ID, basically, so that you can learn such information. And the current version of, for example, Linux doesn't do that. They randomize the IP ID per session or per connection. And the ones that, for example, I use is like Windows XP or FreeBSD, and we still have 22.7 million of them. And I have to say, this is an example of a side channel. We have actually many more side channels. That by itself suggests that when we design our protocols, we didn't think about privacy and security. So here you are. We have shared resources that we can use, but I'm very thankful of them. So.
Thank you, and thank you for encouraging people to upgrade from Windows XP.
Definitely.
All right, let's thank Laura.